Good boy. Jump.
So, I was scrolling through my feed the other day, and I saw this video of the box jump world record being set by Evan Unger, a fitness expert from Canada. And I thought to myself, I wonder if my dog Charlie's got anything on this guy. You see, Charlie's an insatiable jumper, a veritable bean. Check this out. Wow. So I decided to do an experiment. I'm using a piece of software called Logger Pro that will help me with the analysis. It allows for easily tracking the speeds and positions of objects in videos. Here's that video of Charlie again. I had him do a bunch of jumps, and this was his best one. Since Evan Unger gets to practice all he wants, I figured I'd give Charlie an equivalent advantage. I left this chair here in the shot so I could give Logger Pro an accurate size scale for the video. I measured this distance and found it to be 38 inches. That converts to 96.52 centimeters, and rounded to significant figures in SI units, that's 0.965 meters, which is what I put into Logger Pro. I then went frame by frame and tracked the approximate location of Charlie's center of mass. He's got some distinctive spots around his ribcage, so I tried to follow those. Then, Logger Pro helps by calculating the position versus time and generates some graphs. My first instinct is to look at the average acceleration to check that once he's in the air, it matches that of the acceleration due to gravity on Earth, which is 9.8 meters per second squared. Since once he's in the air, Charlie's in free fall, he'll only be under the effects of gravity. You can see that once Charlie's jumping motion is over and he's sailing through the air, the average value analysis shows 9.984 meters per second squared in the downward direction. This is really close to that 9.8 we were looking for, and it's possible the discrepancy could be explained solely from the discretization of the digital video. We now have an idea of how much error Logger Pro's calculations might have. Subtracting our expected from our measured and dividing that by the expected value, rounded to significant figures, looks like about 1.805%. That's pretty good. We can also see this nice parabolic shape in blue that indicates Charlie's up and down or vertical motion. The red here indicates his side to side or horizontal motion. He did twist a little in the air, but the analysis of torque forces is a little bit beyond the scope of this video, and his horizontal motion won't affect his vertical motion. If we look at the arc on the video itself and analyze it like a one-dimensional motion diagram, it's easy to see that he started out going faster at the bottom, and as he gets to the top, the dots get closer, meaning he's moving a shorter distance over the same amount of time, which indicates a slower speed. Then his motion changes direction and he speeds up again. This matches the model for free fall motion. We can even see that at the same vertical positions going up and down, the space between the dots is almost exactly the same. These two and these two, meaning his velocity has the same magnitude even though he's moving in a different direction, which is what we expect from freefall motion. Let's look next at Charlie's velocity graph. This portion of the motion is when he's winding up and then doing his actual jump. His highest velocity is going to be the instant his feet leave the ground, because after that he's in freefall and only under the influence of gravity, which will slow him down and turn him around as we were just discussing. His max velocity is shown here to be almost 3 meters per second. If we check the table, it reads about 2.9. The downward slope of this velocity graph is then going to show his downward acceleration, that 9.8 meters per second squared due to gravity we talked about earlier. And again, it's very close, almost the same, 9.944. Here, where his velocity is right at zero, is the very top of the arc of his motion, where he stops for an instant. Then he starts speeding back up again, going in the downward direction, reaching the same magnitude he left the ground at. Logger Pro again here shows about 2.9, but negative this time because he's moving downwards. We could also use Logger Pro to analyze Charlie's average acceleration during his actual jump. In this portion of his jump, his mean acceleration was 8.24 meters per second squared over the course of this time period, which was 2.9 seconds to 4.3 seconds, a period of 1.4 seconds. In order to do our force analysis, we need to have a mass. So I took Charlie to the vet to have him weighed, and their scale read 25.6 pounds, which converts to 11.6 kilograms. Since we know F equals ma, we can calculate the total force Charlie's legs generated during this jump. M equals 11.6 kilograms, A equals 8.24 meters per second squared, and M times A is going to equal 95.6 newtons. To find his generated momentum, we can multiply this by the number of seconds the jump took, which was 1.4 seconds. This gives Charlie a total generated momentum of 134 newton seconds. The last bit I'm going to need for the analysis is his leg length. I measured Charlie's legs from toe to hip, and it came out to 13.25 inches, which converts to 0.3366 meters. All right, let's bring up the stats. Charlie. Leg length, 0.3366 meters. Mass, 11.6 kilograms. Max velocity, 2.9 meters per second. Max acceleration, 15.59 meters per second squared. Average acceleration during jump, 8.23 meters per second squared. Average force during jump, 95.6 newtons. Generated momentum, 134 newton seconds. Now, since Evan has more mass than Charlie, and he jumps higher than Charlie, his generated force will almost definitely be higher than Charlie's. But I want to look at how energy dense their muscles are. How much acceleration can their legs provide per kilogram of body mass? Charlie's legs are much shorter compared to the rest of his body too, so it might be useful to look at how much acceleration their legs can provide compared to the length of their legs. Let's look at the numbers that really matter to Charlie in this competition. Average acceleration to mass ratio, 0.709 meters per second squared per kilogram. Average acceleration to leg ratio, 24.5 meters per second squared per meter of leg length. All right, let's hope Charlie's numbers hold up. Now, let's move on to Evan Unger. The video of this jump was hand shot and pans up at the end, so I had it stabilized for Lager Pro's analysis. Evan's world record-breaking jump came in at 163 centimeters, the height of this platform. So that's the height I'll be using for Lager Pro's reference during its analysis here. Again, I went frame by frame and tracked the approximate location of Evan's center of mass. Evan's jump is different than Charlie's because he doesn't come back down. In order to effectively maximize his highest jump, he should reach a vertical velocity of 0 at the exact time he lands, which we do sort of see here. His velocity is actually still positive, so my guess is he could have squeezed an extra centimeter or a half out of this jump. Let's also double check, as we did with Charlie, what the margin of error looks like here by comparing his measured free fall acceleration with that of our expected acceleration due to gravity. Here, it shows 9.810 meters per second squared, resulting in an almost negligible amount of error, 0.06%. That's even better than the 1.8% from Charlie's analysis. Now, looking at the acceleration during his actual jump, we can see an impressive average of 10.72 meters per second squared over the course of 0.49 seconds. The table over here shows the max acceleration of 15.92 meters per second squared. That's actually shockingly close to Charlie's 15.59, and while his average is much higher, his jump takes a much shorter period of time than Charlie's did, so his maximum velocity only gets up to 3.495 meters per second. That's only about half a meter per second more than Charlie. In order to do the force analysis, we need Evan's weight, but it's not in the Guinness press release, so I found him on Facebook and slid in his DMs. He's 174 pounds, ringing in at 78.9 kilograms. Now we can calculate the total force Evan generated during his world record-breaking jump. M equals 78.9 kilograms, A equals 10.72 meters per second squared, and M times A is going to equal 846 newtons. That's really impressive. But to find his total generated momentum, we have to remember he only did this for 0.49 seconds, so his momentum is going to be less than the average force. Still an impressive 414 newton seconds. The last bit we need for the analysis is his leg length. Evan's height at the time of the jump is 5 foot 10.5 inches, which is almost exactly 1.79 meters. I used a ruler and measured this still image. Converting the ratio of his actual height to this measurement of his height to find the length of his legs, which came out to 1.03 meters. All right, let's bring up the stats. Evan came in with some impressive numbers. Leg length, 1.03 meters. Mass, 78.9 kilograms. Max velocity, 3.495 meters per second. Max acceleration, 15.92 meters per second squared. Average acceleration during jump, 10.72 meters per second squared. Average force during jump, 846 newtons. Generated momentum, 414 newton seconds. As predicted, Evan's force analysis blows Charlie's away. Evan generated a total force of 414 newtons versus only 134 newtons for Charlie. But let's remember that we're trying to find how effective these jumpers' legs are compared to their total masses and the length of their legs. Let's see the numbers that truly matter to Evan in this competition. Average acceleration to mass ratio, 0.136 meters per second squared per kilogram. Average acceleration to leg length ratio, 10.4 meters per second squared per meter of leg length. How did that compare to Charlie? Sorry, Evan. Better luck next time. Even though you generated 3 times the momentum as Charlie did, Charlie provided 2.5 times the acceleration you did per leg length, and more than 5 times the acceleration per kilogram of body weight. The winner is clear. It's Charlie.